This presentation is about our final project for CSE6250 Big Data Analytics for Healthcare. I'm Luke Wicent and I will be presenting this report on behalf of my groupmates Jinmiao, Huang, and Cesar Osorio. Our project is titled Learning to Diagnose Using Clinical Notes. The goal of our project is to apply big data and deep learning-based NLP frameworks to automatically assign clinical ICD-9 codes to clinical notes. We believe this is important because EHR data captures a variety of patient clinical information, and having the clinicians better understand EHR simply means better healthcare delivery. Since 80% of all healthcare record data is in unstructured text, we believe that if we can leverage technology to extract information from this wealth of data, we can help the clinicians further their understanding and ultimately improve healthcare delivery. Here's a sample of a clinical note. Clinical notes include information about symptoms, psychological state, and other procedures that may not be included in other parts of the mimicry database. Hence, we believe that this is a rich source of new features to automatically predict ICD-9 code or category. For this project, we use the mimicry database and focus our analysis on the category discharge summaries, as it contains actual ground truth and free text compared to other categories. Here's an overview of our methodology. First, we will do some data pre-processing, followed by feature extraction, and then lastly some model training and testing. Note that we'll limit our problem here into classifying only the top 10 or top 50 ICD-9 code or ICD-9 categories. For the data pre-processing, we extracted the relevant data from the mimicry database. We removed the stop words and match the corresponding label for each hospital admission. Now for the feature extraction methods, we tried TF-IDF, word-to-vec, and word sequences. TF-IDF, or term frequency inverse document frequency, evaluates how important a word is to a document in a collection of documents. For word-to-vec, we use the continuous bag of words architecture, which predicts the target word based on the context. We created a word-to-vec model from the mimicry corpus, and we also tried using pre-trained word vectors induced from PubMed. We used the word sequence in each admission text note as our sequence input for our deep learning models. We tried the different configurations shown here in our experiments. So in this study, we created 3 baseline models, namely linear regression, random forest, and feed-forward neural networks. For logistic regression and random forest, we had 1 classifier per label, while for the neural network, we adapt the algorithm to perform multi-label classification in its full form, so we only have 1 classifier for all the labels. We experimented on the models under the different configurations as shown. Recently, CNN have shown excellent results for NLP, such as semantic parsing, search query retrieval, and sentence classification. Hence, we also tried it here. We tried it under the different configurations as shown here, with inputs using the word sequence plus word-to-vec embedding matrix. The training time was around less than 30 minutes in the Azure NC24 environment. In addition, we also experimented on LSTM and GRU RNNs. We used the same kind of input in CNN. We tried the different configurations as shown, and the training time was around 6 to 18 hours on the Azure virtual machines. So we used precision recall and F1 and accuracy as metrics for our multi-label classification problem. Because of the highly imbalanced nature of the dataset, you can see here in the table that even from a model that always outputs 0, a very trivial model, the accuracy is very high. Therefore, we focus on just increasing the precision, recall, and F1. Tuning the feature extraction methods and model configurations here shows our best performance for each model. The results are ordered from best to worst. For both top 10 code and category classification, GRU produced the best result at around 0.69 and 0.53 F1. LSTM and GRU were both better than our baseline models, implying that this Our deep learning models were able to extract information from the word sequence that was otherwise lost in non-sequential models. CNN also showed somewhat similar performance to LSTM and GRU, but at a much shorter training time. For the top 50 code and category classification, unfortunately our deep learning models were unable to beat the baseline models. Here shows the precision and recall curve for the top 10 and top 50 model. I would like to take note of label 46 and label 44. They were able to produce good performance in spite of having fewer occurrences. Although not done here, further analysis on why is this the case is highly recommended. To conclude, we were able to use deep learning methods to produce better results than our baseline models. We hope that our deep learning implementations could serve as a baseline for future work. Here are some suggestions for future work, and thank you for listening.